Hello everyone, and welcome to our video on vector fields. So let's start out with a definition. Let D be a set in R2, that's a plane region. A vector field on R2 is a function f that assigns to each point x, y, in D a two-dimensional vector f of x, y. So we represent vector fields with arrows drawn from their corresponding points. So if we take a look at this graph, what this is saying is at each x and y coordinate, there's a vector coming off of that x and y coordinate. And the direction and size of this vector tells you graphically the value of the gradient field at that point. All right, so another definition, let E be a set in R3. A vector field on R3 is a function f that assigns to each point x, y, z in D a three-dimensional vector f of x, y, z. Now these are a little bit harder to draw, but we'll see a simple example of drawing a three-dimensional vector field like this in a short bit. So typically, we express vector fields in terms of their components. So that is the vector field f of xy equals p of xy I plus q of xy j. Or we can write this in our angle bracket notation. So this is the vector p of xy, q of xy. Obviously, if we're talking about a three-dimensional vector field, we would just extend this in the natural way, adding a kth coordinate here. So you get plus r of x, y, z, k, and in vector form, it's the vector, or the angle bracket form, it's the vector of p, q, and r, respectively. Okay, so another definition, vector fields that represent forces are called force fields. So nothing too crazy there, pretty straightforward. So let's go ahead and tackle an example. We're just going to sketch this vector field for f, which is equal to yi plus x plus yj. So we're going to plot a few different values here, but the process is fairly straightforward. So what we're going to do is look at a few x and y values. So let's start with the simplest one, 0, 0. Well, that gives us the 0 vector here. So there's really nothing to draw, right? Okay, what about when we just increase y by 1? We get 1, 1. And let's increase that again to 2. Then we get 2, 2. And for good measure, let's just go to 0, negative 1. That's going to give us negative 1, negative 1. And so we're just going to, at these points, graph these vectors. So here at 0, 1, so x is 0, y is 1. We're going to go over 1, up 1. That's going to be our vector here. And at 0, 2, our vector is going to go over 2, up 2. So it's the same direction, but just a greater magnitude. Okay, and if we go down to 0, negative 1, we get negative 1, negative 1. So here, go down 1, left 1. And I think it's pretty clear to see that if we went down one more, we would go like this. So you can kind of see what's happening already on the y-axis, which is that basically your vectors are just growing larger as you go up the y-axis. And same thing on when you go down, they're pointing the same direction, but the further down you get, the longer your vectors grow. Okay, so let's plot just a few more to see kind of what happens when we go left and right here. Now, of course, there's no rule that says you have to only plot things on the x or y axis. I just think that's a good starting point for getting a general idea of the vector field. So 1, 0 gives us what? We get 0, 1. And now when x is 2, we get 0, 2. And let's go with -1 and -2. So that gives us 0, -1 and 0, -2. Okay, so at 1, 0, our vector goes just to the right by 1. Or sorry, just goes up 1, not to the right. So our vector goes straight up a distance of 1. And at 0, 2, or at 2, 0, it goes right 0, up 2. And for these points on the left side, basically the same thing, except our vectors are going down. And for good measure, let's just plot like 2 more. So we're plotting quite a few here. Normally I'd be pretty happy with somewhere around 5, 6, 7 to get a picture, but 10 is a pretty good picture. You should usually be pretty happy with that. All right, let's try when x is -1 and y is 1. That gives us 1, 0 for our vector. So we go right 1, and that's it. And the last one I'm going to draw for now. Oops. Is going to be, let's go with x is 1, y is -1. So that gives us -1, 0. So that vector looks like that. Okay, so that should hopefully give you a pretty good idea of how to draw these vector fields. There's nothing too crazy going on here. So now this one's a little bit tougher. Sketch the vector field in R3. But actually, if we think carefully about what this vector field is, it's pretty easy to draw. It's just conceptually doing anything in 3 dimensions is always a little bit harder to wrap your head around. Okay, so our vector field here is just z times k. So in other words, this is the vector 0, 0, z. That means this is a vector, each vector only moves up, and it moves up a distance equal to its z coordinate. So if we look at the xy plane, all the vectors would be 0, because z would be 0. But if we look at when z equals 1, what do we get there? Well, we get a bunch of vectors that go 0, 0, 1. It's a little tough to draw ones that are not in alignment there. So let's see, something like that. So basically the idea here is just to recognize if you've got the plane z equals 1, all your vectors are going to be 1. And then the further up you go, so when I get to z equals 2, then all my vectors are going to be still straight up, but they're going up a distance of 2. Okay, that's good enough to convey the idea here. Okay, so now let's talk about one of the results we can get from understanding these gradient vector fields, which is Newton's law of gravitation. So Newton's law of gravitation gives us that the magnitude of the force for gravity is equal to little m times big M times capital G over r squared, where Little m and big M are the masses of the two objects, r is the distance between them, and g is the gravitational constant, which is given here. So let's consider mass to be the object centered at the origin, or the mass of capital M, I should say, to be the object centered at the origin. Let the position vector of the object with mass little m to be x bar equals xyz. Then the radius, r, the distance between them, so we can think of this like a radius coming out from the origin. Whatever that distance is the magnitude of the vector x here that we've positioned for our second object. And therefore, r squared is just the magnitude of that vector squared. The gravitational force exerted on the second object acts towards the origin, right? So we've placed our object m here at the origin, and there's this other little m object. So gravitational force is pulling this way. So first of all, we should think of why do we model it this way? Well, usually it's because we have one object whose mass is so much larger that the force relative to the object is much greater. So you don't think of the moon moving the Earth, you think of the Earth moving the moon, even though technically both objects are really moving each other at any given time. It just makes a little more sense since the impact overall, or relatively speaking, is much greater from the larger object. Okay, so the gravitational force exerted on the second object acts towards the origin and has a unit vector in the direction given by negative the vector to x, so the vector out this way is the vector x. So it has a unit vector negative the vector x divided by its magnitude. Therefore, the gravitational force acting on the object is found by multiplying the magnitude of the force, which is this, times the unit vector in the direction of the force, which is this. So altogether, that gives us the gravitational field, which is the vector field F equals negative little m big M times g divided by the magnitude of x cubed times the vector x. All right, so definition. If f is a scalar function of two variables, recall that its gradient is defined by the gradient of f of xy equals the partial derivative with respect to x times I plus the partial derivative with respect to y times j. And for three variables, it's defined the same way, except we extend the third coordinate is the partial derivative with respect to z times k. The gradient of f is a vector field, and we call it the gradient vector field of f. Okay, so let's take a look at an example. Find the gradient vector field of f of xy equal to y minus x cubed. Plot the gradient vector field together with a contour map of f. Okay, so the first thing I'm going to do is the contour map part. Let me just make sure I put this at a scale that kind of matches what I need. Okay, that should be good enough, I think. Okay, so for the vector field, if we want to draw some level curves, we're just going to call f of xy some constant k. So k equals y minus x cubed. And so I can rewrite this as y equals x cubed plus k. So this is going to look like a cubic function for various values of k. So that's what our level curves look like. So at 0, 0, we get 0 for k equal to 0. And then what does our graph go? Well, that graph actually looks not appropriately scaled. Let's try that again. I want to make sure the shape at least makes some sense here. Otherwise, this problem won't be all that helpful. Okay, that seems a little bit better. Okay, so when x is 1, so if we take k equal to 0, so again, k equals 0, so y equals x cubed, we get 1, 1, and negative 1, negative 1. And the graph kind of sharply curves upwards. It starts out kind of level and then curves sharply. And then at 2, we'd be all the way up at 8. Well, my picture's not perfect, but hopefully it's close enough. So this is what we get when k equals 0. So let's look at just a couple different values here. So if k equals 1, that's just going to shift this graph up to 1. So keep in mind, what does this mean? This is the values where the function is equal to 0. So this is the x and y values where the function equals 0. And similarly, if I shift this graph up 1, I get that f of xy equals 1 on this curve. And let's just do one more for good measure. So negative 1. It's going to look something like that. Okay. So there's 3 level curves for our graph, and we can kind of see pretty obviously how the graph is going to go from here. So now let's take a look at the gradient vector field. So the gradient of f is the partial derivative with respect to x, which will be negative 3x squared. And the partial derivative with respect to y, which is just going to be 1. So if I take x equals 0, I get that the gradient of f equals negative 3, or sorry, just 0, 1. And then when the x equals 1, the gradient of f is going to be equal to negative 3, 1. And so notice that this gradient is only dependent on x. That's not always going to be the case, for sure. It could be dependent on both x and y. But in this case, it's only dependent on x, and we'll see what that means in terms of the picture momentarily. Okay, so if x equals negative 1, that gives us negative 3 times 1, so still negative 3, 1. Okay, so let's try to graph some of these. We'll graph these ones in red, I think. All right, so what this means is whenever x is 0, the gradient is 0, 1. So at all of these points on the level curves, this gradient field is pointing straight up. And whenever x is equal to 1, we get negative 3, 1. So I'm not going to draw this one perfectly to scale, but I do want to keep the slope correct. So we're going to start here and go 1, 2, 3, up 1. So I'm just going to roughly get that there. All right, and when x is negative 1, we get the same sloped vectors. So I'm just going to try to get them close. It doesn't have to be perfect. Okay, the point here is twofold. First is to recognize that there's some sort of relationship happening here between the gradient vector field and the contour map. Second is to remember what that is, actually. So when we talked about the gradient before, we noticed that the gradient vectors always point in the direction of fastest increase. of the function. So how would I travel the shortest distance to get the biggest increase in the value of function? And that as we discussed at that time, is always perpendicular to the level curves. So your fastest rate of growth is always perpendicular to wherever your level curves are. And that's exactly what we see here. All of these gradient vectors are perpendicular to the curves at the point. I may not have drawn them perfectly, but that is the case. So hopefully that helps tie this into what we've already learned about gradient vectors. Now let's just talk about one last little fact here. So definition, a vector field F is called a conservative vector field if it is the gradient of some scalar function, that is, that there exists a function f such that the vector field f equals the gradient of a function little f. The function little f is called a potential function for f. So we'll deal more with these potential functions and these gradient vector fields in the next couple of sections. So we're not going to talk too much about that right now, but that's going to be a big topic moving forward. And just a little fact here that the gravitational field is conservative, meaning that it is a vector field which is defined by the gradient of some function of x, y, and z. Okay, well, that's it for 13.1. Thank you for watching.